Hello, my name is Soheil Kianzad, and I'm a fourth-year PhD student in computer science at the University of British Columbia. And today, I'm glad to present our work with my colleagues at Spin Lab. The title of my talk is PHasking on Paper, Accessing a Continuum of Physically Assisted Sketching. I'll start with a conceptual framework for PHasking, which highlights fluid transition control sharing from assisted to freehand drawing, making use of different types of constraint. And then I will explain our force feedback device capable of implementing this framework. The PHasking pen, unlike other physical assistant drawing tools, uses an untethered ballpoint drive mechanism which produces force by driving a contact ball over a surface. Friction between the ball and surface provides ground back to the user's hands. Using haptic constraints, PowerPen can support computer-assisted sketching and potentially improve users' quality of drawing. But what is the need for such a device? If you happen to walk by an art supply store, you will see a different world, full of brushes, markers, pen, papers, and so on. A world which is completely different from the digital art and graphics, the world of physical art. Physical drawing, in particular either on paper, canvas, or large surfaces such as wall, is still highly valued because of originality, authorship, personal narrative aspects, and continuity of expression. The freedom and functional control afforded by physical drawing is unmatched in electronic media. Meanwhile, freehand drawing is poorly supported in graphical and CAD environments. Also, it is laborious to move fluidly between paper and digital media. We consider different usage scenarios where the physical drawing can benefit from the computer assistant. Later, this will help us to prioritize feature development and consider them in our evaluation. The first scenario was learning to sketch. Learners may be children, hobbyists, or recovering stroke patients. All may need assistance in drawing a straight line, getting proportions right for an animal or a face, or figuring out perspectives. The second example was rapid technical sketching. Rapid sketching is a fast and flexible method of communicating ideas visually. There exist some difficulties with using traditional drawing tools. It is difficult to keep proportions right, and scaling and orienting geometries require time and effort. Different types of drawing aids may be used for large-scale drawing. For example, making straight lines and smooth curves. Designers use tapes to address these physical needs. There are some solutions to help users with their physical drawing. However, for the most of the cases, the computer takes the full control to achieve more accurate drawing. In fact, if you don't want to share the authorship, a printer can do a better job than drawing robots. To explore the use of active force feedback in paper sketching, we present PHasking concept. We introduce PHasking framework, which provides a fluid transition of control sharing from assisted to freehand drawing, making use of different types of constraint. In active constraint, a force field draws the user in a particular direction or rate, and requires an active force feedback device. It always entails active guidance. In passive constraint, movement is free up to the boundary, then constraint. A binary boundary, no shared control, could be implemented with a passive force device, example a brake, because it just prevents the user from going somewhere. Y-axis denotes the strength of the given system's constraint. PHasking can fluidly access all points on this axis by bearing down on the pen tip while drawing. PHasking framework is based on two key interaction concepts, constraint and control sharing. For constraints, PHasking brings a bound system captures and extends the range of assistance explored in the previous work by accessing an interactive constructible virtual environment. The user can place a structure into the virtual environment to constrain their movement both passively and actively, and can interact with the constraints and the sketch itself. In control sharing, users can fluidly move between levels of assistance simply by bearing down on the pen tip. PHasking differs from adaptive force feedback, where the system chooses the degree of assistance based on the user performance. PHasking gives this choice to the user. We articulate the foundational activities which our framework needed to support. We made a PHasking pen to support our conceptual framework, which consists of four main components: a digital pen, a processing core, an orientation sensor, and a ballpoint drive. A digital pen provides us with position sensing and a pressure sensing. The processing core was a Raspberry Pi which runs our CAD software. We use an orientation sensor to sense the orientation angles. roll, pitch, and yaw. And a key driving mechanism was a ballpoint drive, a rolling ball driven by 4 DC motors that provides active and passive constraint during the drawing. We have done several iterations on the ballpoint drive to meet our needs. From left, you can see that the early version with plastic gear between motors and rollers and the rubber connecting ball between roller and the surface contact ball. The second example uses pulley and belt connection between motors and roller. Then we move towards using metal gears between motors and roller for a lower gear ratio of 1:1. Then we optimize the gear ratio to 4:1 to achieve a higher gear ratio and customize our systems for better force feedback. To implement the PHasking pen drawing functions, we developed a simple 2D CAD software system using Python and the PyQt library, which runs on the pen's Raspberry Pi controller. With this software, the user can either free draw or access primitive CAD functions by clicking on a paper tool palette. We use PHasking primitives to construct basic shapes and constraints and perspective functions to use with other primitives. A key part of our PHasking framework is shared control, which brings the following advantage to a collaborating drawing. It improves the speed and accuracy of human-system collaborative tasks, lower the need for visual involvement and control effort, and support expressive drawing on a screen. We have drawn from these functions and expressive approaches to form our own control sharing method. As you can see, the left circle shows how a PHasking pen guides the user to draw a circle, and in the right, user can use the shared control to violate the guides. The color coding shows the pressure profile, where the blue means PHasking pen takes the control and yellow means the user takes control. Before running any usability study, we have to check the viability of the system. We have done a performance characterization using a Bose tensile test setup. The graph on the top right shows the maximum output force response to the PWM voltage pulses, and the graph below presents the force tracking response to a slow sinusoidal PWM excitation. Position control test setup. The PHasking pen's shaft is held in a vise with roll and pitch disturbance applied at the top of the shaft and through the contact ball respectively. The onboard processor controls the contact ball trajectory using orientation, roll, pitch, yaw, and internal ball motion. An external trackball measures ball movement relatively to a global reference. To assess performance, we compare error between command and externally measured trajectories. The result shows that the system responds to rapid yaw changes at 0.5 Hz 35 peak-to-peak angle over 22 seconds, mimicking the significance wrist rotation. When the user rotates his or her hand, the controller needs to compensate the twist movement of the stylus to make it stick to the flat X trajectory as much as possible. We ran a user study with 7 novices and 3 expert participants. 7 tasks are used for the user study, listed here in the order of complexity and execution. The 3 expert participants are architects who sketch in their professional work. A complete session with a novice participant takes 30 minutes. A 30-minute interview was carried out with each participant following the task-based interaction period. In total, participants performed 204 trials. PHasking drawing improved the precision compared to the manual drawing as shown here. After the task, all participants were asked to complete the Likert scale from 1 to 7 on how likely are you going to use this system again in the future, and would you use this feature again, assume a more refined version of the tool for each of the line, rectangle, circle, and shared control. We asked if the movement and speed and force is appropriate for the users. The participant responses were mostly positive. Participants are positive that the PHasking pen will improve their productivity if the device is smaller and more precise. We received insightful comments from the expert participating during the interviews. While estimating hand drawing as 1 to 10% of their entire process, after which continuity and precision required CAD, they wished for more. Also, participants expressed that they were positive on productivity using our system. In conclusion, we find out that our prototype was sufficient to assess a PHasking potential. The concept found an enthusiastic reception and feedback points to key improvements. We find out about the interesting functions within this framework, including modifying elements, resize, rotate, amend, as well as copy, paste, and we identify free-drawn marks as parametric objects. Also, we find that it's a small, straightforward step to full digital twinning, where we can modify it on a screen, then bring it back to the paper with guided tracing. Thank you for your time and attention.